Fundamental of Physics. PHY 145. Chapter 8. Heat. What we will learn. Understanding temperature, heat, and thermal equilibrium. Heat capacity and specific heat capacity. Phase transition. Latent heat. Calorimetry, conservation of heat energy. 8.1, Temperature, Heat, and Thermal Equilibrium. 8.1.1, Temperature. Temperature is defined as a measure of hotness, or coldness of a material. A more scientific description of temperature is, that it is a measure of the average kinetic energy of the molecules, that are in a material. Thermometer is instruments designed to measure the temperature. There are three temperature scales that are commonly used: Fahrenheit scale, Celsius scale, and Kelvin scale. Figure 8.1 shows several important temperature readings for each temperature scale. Temperature scales between Fahrenheit, Celsius and Kelvin. Several important temperature readings for each temperature scale. Example: the boiling point of water is 100 degrees Celsius, or equals to 212 degrees Fahrenheit, or equals to 373.15 Kelvin. The freezing point of water is 0 degrees Celsius, or equals to 32 degrees Fahrenheit, or equals to 273.15 Kelvin. Temperature conversion, between Fahrenheit, Celsius and Kelvin. 1. Celsius to Fahrenheit, temperature in Fahrenheit, TF, equals 9/5, temperature in Celsius, TC, plus 32. 2. Fahrenheit to Celsius, temperature in Celsius, TC, equals 5/9 times, TF minus 32. 3. Celsius to Kelvin, temperature in Kelvin, TK, equals TC plus 273.15. 8.1.2, Heat. Heat is defined as a flow of energy between two objects or systems, due to a temperature difference between them. Heat flows from a system of higher temperature, to one at lower temperature. Heat can be transferred to, or from, a system in three distinct ways: conduction, convection or radiation. Heat is a type of energy. So the SI unit for heat is joule. Other common unit used for heat is calorie. The conversion factor between joule and calorie is 1 calorie equals 4.187 joule. 8.1.3, Thermal equilibrium. When two objects at different temperatures are in thermal contact, a flow of energy from the hot object to the cold object will occur. Object that loses energy will become colder, whereas object that gain energy will become hotter. The flow of energy stops once the temperatures of both objects are the same. Both objects are said to be in thermal equilibrium. If temperature A is higher than temperature B, heat transfer from A to B. Body A that loses heat, temperature decrease. Body B that gain heat, temperature increase. When temperature A is equal to temperature B, no heat exchange. This condition called thermal equilibrium. Heat capacity, and specific heat capacity. Heat capacity. The amount of heat, Q, that flows into or out of the system, is directly proportional to the temperature change of the system, delta T. In mathematical, it can be write as Q directly proportional to delta T, or Q equals C times delta T, or C equals Q over delta T, where C equals the constant proportionality, or we called heat capacity of substance. The SI unit for C is Joule per degree Celsius, or Joule per Kelvin. So, heat capacity is defined as the quantity of heat needed to raise the temperature of substance by 1 degree Celsius or 1 Kelvin. Specific heat capacity. A greater amount of heat is also required to raise the temperature of a greater mass of material. So, the heat capacity of a substance, C, is directly proportional to the mass of the substance, m. In mathematical, it can be write as heat capacity directly proportional to m, or heat capacity equals C times m, or C equals heat capacity over m equals Q over m times delta T, where C equals specific heat capacity of substance. The SI unit for C is Joule per kilogram per degree Celsius, or Joule per kilogram per Kelvin. So, specific heat capacity is defined as the quantity of heat required to change the temperature of 1 kilogram of substance by 1 degree Celsius, or 1 Kelvin. Phase transition. A material can exist in solid, liquid or gas phase. When a material gains or loses heat, the temperature of the material will increases or decreases. But sometimes temperature remain constant, even though heat is being transferred. This happened during change of phase or phase transition. During phase transition, the physical characteristic of substance change from one to another. Phase changes such as 1. Solid to liquid, melting process, or liquid to solid, freezing process. 2. Liquid to gas, vaporizing process, or gas to liquid, condensing process. During a phase transition, the temperature of the object remains constant. Phase change involve change in internal energy. Latent heat. Latent heat, L, is defined as the heat required to change a phase, a unit mass of substance. L equals Q over M, or Q equals M times L, where L equals latent heat, and M equals mass. The SI unit for L is Joule per kg. For solid to liquid, or liquid to solid phase transition, it is called latent heat of fusion, LF. For liquid to gas or gas to liquid phase transition, it is called latent heat of vaporization, LV. Calorimetry, application of conservation of heat energy. Calorimetry is the technique for measuring specific heat capacity of material. Figure 8.1 shows calorimeter that used to determine the specific heat capacity of material. The amount of energy that leaves the sample, equal to the amount of energy that enters the water and calorimeter. Conservation of heat energy. The principle of conservation of heat energy. For the system completely isolated, the amount of heat lost from a system, Q loss, must equal the amount of heat added to the system, Q gain. Or can be simplified as heat loss equals to heat gain. Example. Experiment to determine the specific heat of metal block, alloy. Add a hot metal block to the water in the calorimeter. The main concept is heat loss equals to heat gain. Heat loss by alloy equals to heat gain by water, plus heat gained by calorimeter cup. Q alloy equals to Q water plus Q calorimeter.